So far we were discussing infinite series of positive terms, and we had discussed how to find the convergence and divergence of a given infinite series using the direct comparison test, the limit comparison test, and so on. So, in this class we will be discussing more on series which may not be restricted to the terms, or the terms of the series may not be restricted to be positive. It can be negative as well as positive. So, welcome to this session where we discuss the alternating series of real numbers. The definition of alternating series is as follows. The series summation n equal to 1 to infinity negative 1 power n u n or summation n equal to 1 to infinity negative 1 power n plus 1 u n, where each u n is greater than 0 is called an alternating series. So, we can expand these terms for a clear understanding. Summation n equal to 1 to infinity negative 1 power n u n. If we put the values from n equal to 1 to infinity here, you will be getting negative u1 plus u2 minus u3 plus u4 and so on. So, we can see that the sign of the terms are alternatively positive and negative. That is why the series is called an alternating series. The second notation was summation n equal to negative 1 to infinity negative 1 power n plus 1 u n, and if you put n equal to 1 to infinity, in this case you will be getting it as u1 minus u2 plus u3 minus u4 and so on, where also we can see the terms of the series are alternatively positive and negative. So, if the first term is negative, we will use this notation. If the first term is positive, we can use this notation. That is the only difference. Now, what is the relevance of such a series? Why do we require such a series? In what real case or what real situation do we apply this? See, for example, suppose we want to mathematically modeling in the case of mathematically modeling the oscillation of a pendulum of a clock starting from some time say t is equal to t naught. We are looking at the movement of a pendulum of a clock, and we want to find the total displacement of the pendulum from some time say t naught to some time say t1. We know that the pendulum moves in one direction, again goes back to the next opposite direction and then comes. So, if we restrict one direction to be positive, the opposite direction can be taken as a negative direction. So, when you add the displacement of the pendulum together, we have to add all this and add up in which in the positive direction how much we got, in the negative direction how much we got, we have to add it together. So, in such situations we can show it as a alternating series because the directions are different, but total displacement we have to add both. So, that is the case of, there is a practical application. In such situations we can apply this type of alternating series. Now, some examples of alternating series are summation negative 1 power n upon n and summation negative 1 upon n plus 1 n upon 2n plus 1. So, these two are two examples which we consider here. Summation n equal to 1 to infinity negative 1 upon n by n. So, which is equal to negative 1 power n upon n. If you put n equal to 1, we can see it is a negative 1 upon 1. If you put n equal to 2, negative 1 power 2 becomes positive 1. So, that is 1 upon 2 then 1 upon 3 and so on. So, we can see that the terms are alternatively negative and positive, and so this is an alternating series. The next example that we had is summation n equal to 1 to infinity n upon 2n plus 1 minus 1 power n plus 1. So, minus 1 power n plus 1 n upon 2n plus 1. When you put different values of n, we can see this is 1 upon 3 minus 2 upon 5 plus etc. So, again we can see that this is a positive term minus another term plus another term and so on. So, that is also an alternating series. Now, we have studied in the infinite series, in the case of infinite series, we have studied that a series sigma xn converges if the nth term of the series goes to 0 as n tends to infinity. So, let us look at these two examples and let us see whether we can get a similar result here also. So, the nth term of the first series un is equal to 1 by n. So, remember that whenever you write an alternating series, we will be using the expression negative 1 power n un or negative 1 power n plus 1 un, where un was strictly made to be positive, where un is always greater than 0. So, un is always greater than 0. So, that means we are considering un to be the term only, not its sign. So, that is why un is equal to 1 by n for the series summation negative 1 power n upon n. Un is equal to 1 by n. What happens to the nth term? Limit n approaches infinity, 1 by n equal to 0. So, you have to keep this in mind. We will see whether it is applicable for the convergence of the series. And summation negative 1 power n plus 1 n upon 2 n plus 1, the nth term limit n approaching infinity, un in this case is n upon 2 n plus 1. So, limit n tends to infinity, un is equal to limit n approaching infinity n by n into 2 plus 1 upon n. So, n and n will get cancelled. You are getting it as 1 by 2. So, limit n approaching infinity, un is a finite non-zero quantity, and hence we can say this series summation negative 1 power n plus 1 n upon 2 n plus 1 fails to converge, does not converge, does not converge. By which test? By nth term test. So, because the n, what does the nth term test say? If summation un converges, then that implies limit n approaching infinity un is equal to 0. So, if P implies Q, that is logically equivalent to saying negation Q implies negation P. So, if limit n approaching infinity un is not equal to 0, if we are using this notation, we need not write if here. So, if limit n tends to infinity un is not equal to 0, that implies summation un does not converge. So, always some students make it a mistake. If limit n tends to infinity un happens to be equal to 0, they will say that summation un converges, but that is wrong. The counter example is sigma 1 by n. So, limit n approaching infinity un equal to 0 implies summation, does not imply summation un is convergent. Example, the counter example is summation 1 by n, because the nth term un is 1 by n, which goes to 0 as n tends to infinity, but we have seen that this is a divergent series. So, this is a counter example to show this, but in this case we can surely say that because the nth term goes to 1 by 2, which is not equal to 0, this series does not converge. But what about the first series that we have discussed? The first series, for the first series 1 by n was the nth term, and we have shown that limit n tends to infinity 1 by n is equal to 0. So, for this series we cannot apply the nth term test to see whether the series is convergent or not. So, actually we are failing for all the tests that we had studied for convergence of positive term series for this particular case. So, what we have to do is we have to find something new. So, that is what we can see in the next slide. So, the test for convergence says that the second series diverges by the nth term test, but to check the convergence of the first series we need another test which is exclusively for alternating series. And here comes what is the test for alternating series, which is called the Lebanese test. So, what does Lebanese test say? If the alternating series summation n equal to 1 to infinity negative 1 power n plus 1 un, where un's are positive, satisfies two conditions, we can say definitely the series converges. And which are the two conditions? Condition number 1, the terms should be in a decreasing order. So, the terms should descend from the first term. It should decrease, and as n tends to infinity, the nth term should go to 0, or limit of un is equal to 0. So, these two conditions guarantees that the alternating series converges. Otherwise, if one of these fails, then the alternating series diverges. So, that is what Lebanese said. Now, let us look at the why Lebanese had established such a result. Using a picture, we can show that. Suppose you are given an alternating series summation negative 1 power n plus 1 or n plus 1 un. First condition is un plus 1 is less than or equal to un, and second condition is limit n approaching infinity un equal to 0. So, these two conditions should hold. So, using a picture, you can have an idea of what happens in this case. This series is nothing but u1 minus u2 plus u3 minus u4, etc. So, we have seen in the case of infinite series that an infinite series converges if and only if the sequence of partial sums converges. So, let us look at the partial sums of this particular series. So, first case we are starting with some u1. So, let that u1 be somewhere here. So, this is your u1, which is exactly same as your s1, the first partial sum. So, the first partial sum is up to this point. Now, when you take the second partial sum, here we can see that all the un's are positive, all the un's are greater than 0, and so when you take the second partial sum, you are subtracting something from un, subtracting a positive term from un. So, this s2 will be somewhere here. If this is your u2, or this will be your s2, this will be your u2, this will be your u1. So, s2 will be somewhere here, because you have subtracted u2 from u1 to get S2. Then you are adding some positive term. So, it is getting added to a lesser value. Why lesser? Because we have a condition that each un plus 1 is less than or equal to un. So, un plus 1 should definitely be less than un. So, we can move only up to a particular point which is less than S2. So, this is S3. Now, it comes to some S4 somewhere here. Again it will go to somewhere here which is your S5 and it goes on, and ultimately what happens? Your limit n tends to infinity, un is happening to be equal to 0. So, that means the sequence of partial sums has to be somewhere here at last, which is a very negligible interval. So, that means the series as a whole converges to one particular point inside this interval, and that is the main idea or concept in the Lebanese test. So, this is the idea behind Lebanese test. Now, using this Lebanese test, we can see the convergence of this series as example 1. Summation minus 1 power n upon n, which we failed to do using the nth term test. Let us see what happens when we apply the Lebanese test here. So, the given series is example 1. We are going to see summation n equal to 1 to infinity negative 1 power n upon n. So, what is your un? un is equal to 1 upon n. So, obviously, un plus 1 will be 1 upon n plus 1. So, which is greater, n plus 1 or n? N plus 1 is greater than n. Therefore, un plus 1, which is equal to 1 upon n plus 1, is less than 1 by n, which is our un. So, we have established the first condition, un plus 1 is less than un. Now, limit n tends to infinity, we have already seen limit n upon n tends to infinity 1 upon n happens to be equal to 0. So, this was your condition number 2. So, we have satisfied the two required conditions for Lebanese test, and so by Lebanese test what we can say? By alternate convergence test or Lebanese test, we can say summation negative 1 power n upon n converges. So, see, this example is very important because we have already shown that summation 1 by n is a divergent series, but if we apply a negative 1 power n to that, or if we alternate the terms of the series, then that series converges. So, this is a very important example which we will be discussing in the next class also. So, that is how we can show the convergence of this series. So, that completes the example number 1. Now, the second example is test the convergence of the series summation negative 1 power n upon n square plus 1. So, again we can see using Lebanese test what happens. Summation, the question I will read once more, minus 1 power n upon n square plus 1. Okay. So, what is un in this case? un is nothing but n upon n square plus 1. un plus 1 will be replacing n. Wherever there is n, we are going to replace it with n plus 1. So, there is n plus 1 upon n plus 1 the whole square plus 1. So, as we can see from the expressions itself, it is a bit difficult to compare directly because we are having a larger denominator, but the numerator is also getting bigger. So, we cannot at a glance we cannot compare these two. So, we require something more, how to find the increase or decrease of this sequence. So, you can do one thing, you can subtract un plus 1, un from un plus 1. So, that is equal to n plus 1 upon n plus 1 the whole square plus 1 minus n upon n square plus 1, which gives you n plus 1 the whole square plus 1 into n square plus 1. Numerator will be n plus 1 multiplied with n square plus 1 minus n multiplied by n plus 1 the whole square plus 1. So, n square, sorry, what was it? N plus 1 multiplied with n plus 1 multiplied with n square plus 1 minus n multiplied with n plus 1 the whole square plus 1. So, when you simplify these terms, you can see that the denominator remains the same. Numerator, when you manipulate, you will be getting n cube plus n square plus n plus 1 minus of n into, if you want you can expand this term so that it will be easy for you to understand, n square plus 2n plus 2 you will be getting, because inside you will be having n square plus 2n plus 1. So, that is equal to, I am writing only the numerator because the denominator does not make any difference, minus n cube minus 2n square minus 2n. So, we can see that n cube and n cube will get cancelled, divided by the denominator is there. So, that is equal to n square minus 2n square, you will be getting negative n square, plus n minus 2n you will be getting negative n plus 1 all together on the denominator. Now, let us see whether this is positive or negative. Where does n start from? N definitely starts from 1 to infinity because n is a natural number. So, whatever be the value of n, the numerator is minus n square minus n plus 1. The least value which n can take being 1, there remains a negative 1 there. So, whatever be the value of n you are putting, the denominator remains a positive value, but the numerator becomes a negative value. So, the ratio becomes less than 0. So, what does that mean? What was this? It was the difference between un plus 1 and un. This is less than 0, indicates that un plus 1 is less than un. Now, it remains to show the limit n tends to infinity, un is what? So, what is limit n tends to infinity of un for this case? What was our un? Un is n upon n square plus 1. So, limit n tends to infinity, un is equal to limit n tends to infinity n upon n square plus 1, and as we have discussed in the case of in finding how we can find in sequences chapter, we had discussed how we can find limit n tends to infinity. We can take out the maximum powers of n outside. This forces this limit to be equal to limit n tends to infinity 1 upon n into 1 plus 1 by n square, because 1 n and n square will get cancelled, but this n will remain as such, because the power of the numerator is 1 less than that of the denominator. So, as n tends to infinity, the denominator becomes very large, and so as a whole this goes to 0. So, we have satisfied both the conditions of Lebanese test, and hence we can show that this series converges. So, that completes this example 2. The third example is test the convergence of the series negative 1 power n into 1 upon n factorial. So, this also can be done using the Lebanese test itself, and for this question we can do in another method also. We can use the derivative of a function, that also can be done here. by taking f of x to be something like x by x square plus 1, and by taking the derivative and showing that the derivative f prime of x less than 0 as derivative f of f prime of x is less than 0, which is the condition for decreasing function. And so we can see that type also we can do this question. So that can also be done. Now we can look at example 3, the third problem. Summation n equal to 1 to infinity negative 1 power n upon n factorial. So un is equal to 1 upon n factorial. Un plus 1 is equal to 1 upon n plus 1 factorial. So obviously which is larger? Un is larger than un plus 1 because this denominator is larger than this denominator. So un is larger than un plus 1. So that completes the first condition. And second condition, limit n approaches infinity, un is equal to limit n tends to infinity 1 upon n factorial, and that is equal to 0. So we have satisfied both the conditions of Lebanese test. This one is why? Because n plus 1 is greater than n. So n plus 1 factorial is greater than n factorial, because for n factorial we have the multiplication from 1 up to n, whereas for this one n plus 1 factorial we have multiplication from 1 up to n plus 1. So in addition to this you are having an n plus 1 here. So this side becomes much larger. So that is the condition for Lebanese test for this series, and so the Lebanese test is satisfied and hence this is convergent. So in this session what we have discussed is there are some series which alternate in the sign of the terms of the series, and the nth term test is not as such sufficient to test the convergence or divergence of that particular series. And so we study a type of test which is exclusively designed for alternating series, and hence it is also called alternating series test or alternating series convergence test, and that is what is called the Lebanese test, where we require the terms to be decreasing and the limit of the nth term to be equal to 0. So we have seen some of the examples also here. In the next session, we will be discussing more on alternating series and how to test the convergence of that. Thank you.